Welcome back. I hope you enjoyed working on the project from our previous lecture. In this tutorial, we will perform an FFT analysis on the current waveform of a half-wave diode rectifier. Problem statement: simulate a half-wave diode rectifier circuit and perform the following tasks. 1. Use the Fourier block to determine the magnitude and phase angle of the fundamental frequency and the first two harmonic components of the current waveform. 2. Use the following two methods to obtain the harmonic spectrum of the current waveform and calculate the total harmonic distortion value. 1. Write a MATLAB script using the harmonic magnitudes obtained from the Fourier block to generate the harmonic spectrum and calculate the total harmonic distortion. 2. Use the Fourier Analysis tool available in the Power-Gui block to obtain the harmonic spectrum and THD directly. Getting started. So, let's get started. Launch Simulink and open the model we simulated in Lecture 2. Add the required blocks. Go to the Simulation tab and open the Simulink library browser. Type Fourier in the search bar and press Enter. Right-click on the Fourier block and select Add Block to Model. Also, add a display block to the model. Now, type THD in the search bar. Press Enter and add the block to your workspace. Arrange the blocks. Rotate the Fourier block and connect its input to the output of the current measurement block. Connect a display at each output of the Fourier block. Let's rename the display blocks. Also, connect the THD block at the output of the current measurement block. To find the THD in percentage, we need to connect the output of the THD block by a gain block. Let's add a gain block. Also, add a display block. Connect the gain block to the output of the THD block. Rename the display block. Set the value of gain to 100. Open the THD block and set the frequency to 50 Hz. Next, open the Fourier block. Set the frequency to 50 Hz. Set the harmonics from 0 to 3. Type 0:3 on the keyboard. 0 represents the DC component in the waveform, and 1 represents the fundamental component. We will obtain the magnitudes and phases of 4 components, the DC, fundamental, second, and third harmonics. Next, go to the Simulation tab and click Run. So, the THD is 43.66%. And these are the phases and magnitudes of the 4 components. Plotting the harmonic spectrum. Let's now write a program to obtain the harmonic spectrum of the current waveform. Go to the command window. Click the Home tab, and then select New Live Script. We will plot harmonics on the x-axis. So, type x equals, then square brackets. Inside the brackets, type 0, 1, 2, 3. End with a semicolon. And on the y-axis, we will plot the magnitudes. So, type y equals, then square brackets, and inside the brackets, type all the magnitudes, separated by commas. To draw the spectrum, we'll use a bar graph. Type bar, then parentheses. Inside the parentheses, type x, y. Let's label both axes. Next, set the x and y limits. Go to the Live Editor tab and click Run. Here's the bar graph, showing the harmonic spectrum of the current waveform. Since the value of the third harmonic is very low, it may not appear on the graph. You can zoom in to view it. Double-click inside the graph. And then click the zoom in icon. Reconstructing the current waveform. Now, let's retrieve the original current waveform from its harmonics. Go to the Simulink library and add a sine wave block. Also, add a summation block from the Math Operations section. Add a scope to the model. Let's connect the blocks. Open the sine wave block. Enter the magnitudes of the fundamental, second, and third harmonics. For the bias, enter the DC value only in the fundamental component, and set it to 0 for the others. Enter the frequencies of the three components. We have 1, 2, and 3 as the harmonic numbers. Multiply each by 2 pi, then multiply by 50. To get the frequency in radians per second. Enter the phase values in radians. Multiply the phase values by pi over 180. Click OK. Let's simulate the system to observe the result. Open the scope to view the waveform. This waveform is similar to the current waveform of a half-wave rectifier. Let's compare both waveforms. You can retrieve a more accurate waveform by adding more harmonic components. The sine wave block generates all the components. The summation block adds them to reconstruct the current waveform. Using FFT analyzer. Next, let's move to the second method for obtaining the harmonic spectrum and the THD value. Open the scope of the current waveform. Click the gear icon. Go to the Logging tab, check the box, Log Data to Workspace. Rename the variable name. And select Structure with Time from the drop-down menu. Close the window. Now go to Modeling, then to Model Settings. Go to Data Import-Export and disable Single Simulation Output by unchecking the box. Let's start the simulation and wait for it to finish. Open the Power-Gui UI block and select Apps. Then click on the FFT Analyzer button. This is the current waveform. Let's perform an FFT analysis. Set the fundamental frequency to 50 Hz. And click on Compute FFT. Here is the THD value in percentage, same as we obtained using the THD block. Next, click the Export button. Then go to Tools and select Edit Plot. Double-click anywhere inside the plot area to open the Property Inspector. Click on Rulers. Set the Y limits from 0 to 105, and press Enter. Here, the magnitude of the fundamental component is set as 100%. However, the actual magnitude is 15.5 amperes. All other magnitudes are shown as a percentage of the fundamental component. Summary. In this tutorial, we learned how to obtain the harmonic spectrum and the THD value of the current waveform for a half-wave rectifier. your task. Repeat the same procedure for a full-wave diode rectifier. Thank you for joining us.